My name is Daniel Ankilde. I'm the co-founder and CEO of Cognic. And in this series of videos, I want to share some of my thoughts on AI. So I've basically thought about this domain for my whole life. I started getting into machine learning and AI already in my early teenage years. I was fortunate to discover this amazing topic, partly by coincidence, partly through great role models. So I remember picking up my first book on neural networks in 1999 when I was 12 years old. And I'm not going to pretend like I understood much of that book. Like I had basically no idea what any of the equations meant or what most of the text was about. But I remember reading about sort of the concepts of experience and data shaping decision making and understanding how to find signal in noisy data, and it just became my deep fascination. I've been passionate about this topic ever since, and I think it touches on some deeply human things. It makes you wonder, how do we work? How do humans actually tick? What is the process inside our brain that makes us able to so quickly pick up on patterns and understand ambiguous and conflicting information to the extent we can? It also kind of humbles you before the fact that humans are imperfect. There are limitations to what we can do. And that interesting kind of mixture of us being super efficient and in many ways super powerful, but also limited. And how does that compare to what the current generation of machine intelligence is able to do? And where could this take us in the next 5, 10, 50 years? I find that incredibly interesting and fun to discuss. And I want to share some of that with you. To fully understand what's going on, we have to have a better understanding of what the core technology is and what actually the fundamental mission of machine learning is. So the way I see it, to kind of introduce ourselves to the idea of machine learning or AI. So first of all, why do I keep saying machine learning? Well, I recognize that recent development makes AI more legitimate of a phrase. So the idea of replicating intelligence to kind of, it alludes to mirroring whatever it is humans are doing, albeit in an artificial way. Until recently, I've been a strong proponent of calling it machine learning, to be specific about the fact that it's machines that learn. And whatever resemblance to human intelligence this has is still very superficial. Either way, let's settle on, interchangeably using machine learning and AI. For me, the way I see it, the core goal of machine learning is to learn patterns to solve tasks without explicit programming. So humans do this all the time. We have not been taught how to do every single thing we are able to do. We observe from the day we're born, even before then probably, what's going on around us. We are exposed to patterns in using our eyes, our ears, our touch senses. Everything that comes into our brain shapes our understanding of the world, right? The challenge that humans have and that machines have is that we need to be able to solve tasks we've never really seen exactly before. And this is going to be a theme for this entire journey through machine learning is, I think back on sort of, imagine our origin when we were out in the woods picking berries and hunting animals. If every situation we came across was brand new to us all the time, we wouldn't be able to process the information fast enough to make the decisions necessary. Every rabbit would get away and we would eat a bunch of poisonous berries, right? So somehow we have evolved to make sure that when we're faced with a situation, we can relate it to previous experiences in such a way that we can make rapid and accurate decisions. The core thing here is that if you look closely enough at any situation, it is unique. So the way I put it is the problem with reality is that nothing ever happens, at least not twice. And what do I mean by that? Well, imagine you're, again, chasing a rabbit in the woods. There is never going to be the same rabbit running the same path through the woods being chased by the same person twice, ever. There will always be some difference in the path it takes, what the human does, what the terrain is. So if you depend on learning exactly the situation you're going to experience, you will fail, right? Humans have evolved to be robust for quite a lot of changes in our environment. We can cross an intersection on foot, despite it being different than all other intersections we've seen before. We know what a traffic light is. We know where the intended area to cross is. We know kind of how cars work. Sure, if you come into like a totally different country, totally different, culture of driving, maybe rules are obeyed in a different way, it's going to be challenging and different. But for the most part, we can kind of do it based on experience. So for me, the ultimate pursuit, the challenge of machine learning is how do we achieve generalization? So the ability to solve tasks for unseen input that we have not experienced explicitly during training. That is the real challenge. So we're going to keep this in mind as we go through how we arrived at where we are today, to what extent current algorithms have this ability, and why they may or may not have this ability, and what the next bottleneck is to improve even more. But before we go into that, I want to ask myself also, why is this happening now? Like, what has changed in the last, 70 years? We're going to get to the timeline and history, but like, what has changed? What is happening? Well, from my perspective, there's really two things that have powered the recent breakthroughs in AI and machine learning. Number one, compute. We have an abundance of compute today. It's actually still probably a major bottleneck. Arguably, the last 5 years have been all about sort of scaling up data centers in an extremely rapid way to enormous sizes, like huge farms of GPUs with coherent memory. And there's been tons of technical challenges in getting 100 or 200,000 GPUs to collaborate to train a single model. It's been a monumental engineering challenge. And there's some science improvements there on a fundamental level, but mostly it's been an engineering breakthrough. The other part is data. So world volume of data is now measured in zettabytes. So most people have never heard of that unit. Like, we know gigabytes and we kind of know terabytes, and then a few people come across petabytes. And then if you're in the data center business, you're in exabytes. And then if you're like one of the hyperscalers of Microsoft or hyperclouds, Microsoft or Google or Amazon, you're going to start seeing zettabytes. So we're at zettabytes now. And what this means is that the vast majority of data generated this year is generated this year. Like, the area under the curve of historical data is pretty much smaller than this year's amount of data. I haven't done the exact math, but like, you get the idea. basically there's no point in deleting old stuff anymore because the new stuff is going to be so much more significant than whatever we've seen until today in a year or two anyway. And we're going to get back to the critical nature of all this data. Obviously, this is my kind of passion, is the data part. There are those passionate about improving GPU performance, very important. I'm passionate about the data side. And then on the far right of this slide is also an honorable mention of algorithms. So I don't want to dismiss the importance of making kind of scientific breakthroughs on the algorithm side. It's definitely necessary for the field to advance. And probably we're sort of stuck in a local minima right now. Like there's a consolidation of attention on transformers that may be limiting to progress, because I don't think transformers is like the end of machine learning improvement. There's even a famous blog post that I encourage you to read. Richard Sutton, who actually got the Turing Award, which is like the Nobel Prize in computer science this year, he wrote The Bitter Lesson. And the essence of that essay is that he spent all this time trying to figure out fancy algorithms, and then like brute force just kept outperforming. So with enough compute and enough data, most problems can be solved using today's algorithms, maybe. The maybe there is really the real question about predicting the future. Like, how much more juice can we get out of transformers before we hit some inevitable ceiling? Some say we're far from saturating performance. Some say that we are probably on an S-curve. To reason about that, we have to look into a bit more background on machine learning and AI. So first, some history. So you can actually go very far back to see early signs of people thinking about making machines automate work. Like there are early mentions in China from 1,000 years ago, kind of mentioning automata, mechanical automation concepts. And then there was a bit of a dry spell in terms of progress until, I guess, Pascal, who is a famous French mathematician. He developed the first calculator, essentially. It was called the Pascaline after Pascal. It was like a brass-driven machine that could add and subtract. And he created it to help his father, who was a tax collector, to count money faster. But this was an important breakthrough, 1642. That was a big step. So adding on that was like more formalization of logic, Boolean algebra. Now we're at like the 19th century. And then 1801, Jacquard made the first kind of programmable device. And this had punch cards for kind of programming textile mills. So the industrial revolution that happened in France and Britain and parts of Europe basically accelerated this interest in automating work using machines. So in some sense, the steam engine and other things were all designed to limit the need of human labor and increase productivity, which has been a core economic driver forever, basically. The first mention of a robot is actually, that's a Czech word. So robots were first mentioned in the 1920s, became a sort of an image that inspired people to go deeper into machine learning and robotics. So robot became like a great collective phrase that you could communicate with the public about. And you shouldn't underestimate the power of that. Like when something becomes a part of popular culture and the public mind, funding increases and progress usually speeds up. So that brings us to the start of the modern era, I guess, or until this point, it was pretty theoretical and not so close to what we do today. But in the 50s, some of the major first breakthroughs were actually a little bit before then. In 1943, neuroscientists formulated what is known as the first kind of artificial neuron. So the connection to that is going to be quite important over the rest of the 20th century, because artificial neurons have emerged as the leading method to help machines learn patterns from data. So McCulloch and Pitts described a sort of a mathematical model for the brain in 1943. Today we know they had mostly misunderstood how the brain actually works. We're going to get back to that. Like, some of the core ideas in AI and machine learning are based on an understanding of the brain that is just like totally wrong. So possibly we're in a bit of a dead end in that sense, but let's put that aside for the moment. In 1950, Alan Turing created the Turing test, basically the popularization of the idea of like, if you can talk to a machine and not notice that it's a machine, that's a huge breakthrough. So that's kind of butchering it a bit, but basically what the Turing test was about. That brings us to 1956. So I've kept this on the screen here throughout. In 1956, there was the Dartmouth Conference, and it coined essentially the term artificial intelligence. And it was John McCarthy and a bunch of old white men, because it was, that time of human history. Marvin Minsky was there, Claude Shannon, like the geniuses of signals and information theory. Shannon, if you've not studied his work, is like insane. He was well ahead of his time. So these guys, they proposed a 2-month, 10-man study of artificial intelligence. And to give you a sense of how the history of AI has had a lot of false starts, I guess, where like people massively underestimate how much progress can be made, they believe that a significant advance can be made in one or more of the problems of AI by a carefully selected group of scientists during a summer, right? They thought they could solve, natural language and all sorts of problems, humans that were reserved for humans, in a summer in 1956. Clearly, that's not quite what happened. Like, that's coming up on 70 years ago, and I guess today, in the last 5, 6, 7 years, you can argue we've made a huge amount of progress. But it's been an overnight success, kind of 70 years in the making, or more, if you will. So to put this a bit on a timeline, there have been surges followed by dark ages in AI. And that's worth remembering as we think about the coming 10, 20 years. Is this time different? Is there a risk we are exaggerating how far we've come and creating kind of inflated expectations, and there will be a backlash of disappointment? It's very, very hard to tell. Like, it's totally possible we continue on an extremely steep exponential curve, but it's also possible it's an S curve and we will see diminishing progress and sort of a settling in where engineering and business growth is going to be the focus for some period until there are new fundamental breakthroughs in science. Either way, this is kind of the timeline that I think matters, where the origins in the 40s and 50s triggered in the 60s kind of the first golden age. There was a first chatbot, Elisa, came around this time. And it probably also kind of became a golden age because it coincided with a time of rapid growth in GDP in the US. It was post-war. Like, the whole world was very excited about things in the 60s. everything felt possible. People were dreaming about the future, and the general population had vastly improved living conditions in this time. Then there was the first dark age. So the first AI winter or dark age, I guess, came about in the early 70s. So the excitement of the 60s was met now with the harsh reality that like AI had failed to deliver on its promises. Of course, progress had been made, but the promises were just like way up here, and then actual outcomes were not quite as exciting. And this led to both businesses and the government pulling back from investing in this. So this has become known as the first AI winter or the first dark age. Um, you'll notice throughout this history also that the government has played a critical role. And I think, I'm not going to get into today's situation too much, but like funding from agencies like DARPA in the US and UK government and others have been absolutely critical to making progress on the fundamentals of machine learning and AI, sort of the intersection of computer science and neuroscience and the math behind all of this. And no company would ever fund such fundamental research long enough to achieve these breakthroughs. We're totally dependent on public funding for fundamental science research. So you can ask yourself where you think the next similar leap in technology is going to come from, given how science funding is evolving right now. But that's a different set of videos, I guess. So then in the 80s, another golden age started. So we started seeing more commercial success in the 80s again. Probably, again, this kind of coincided with some other trends where computers now became a thing. Companies started getting computers in mainframe computers became more available. Desktop computers started becoming a thing. Even the personal computer, like the proliferation of computers at home increased a lot. And with increased availability of business data in a digital form and availability of computers, you could make more progress. So businesses started getting value, mostly from what was known as like knowledge engineering or expert systems. And these could be used for things like forecasting and inventory management. And it accelerated a bunch of business processes that had suffered from a lot of manual work and very sort of slow progress. This gave people the idea that there was, people extrapolated very aggressively on this progress and thought, oh, now we're going to, replace all workers with computers in the next couple of years. So that didn't happen. Instead, there was a market collapse in 1987. And I think, it's hard to know what is the chicken and the egg here, but basically in the late 80s, early 90s, the second AI winter started. There was a much more pessimism, public funding pulled back, generally just much less excitement about AI again. During this time, though, 80s and 90s, a lot of critical fundamental breakthroughs were made. There is the invention of the backpropagation algorithm. So what is that? Well, you had the idea of a neuron, an artificial neuron, and to kind of give you a super high level idea, the thinking is there is signals coming in, similar to how electricity is transferred through nerves in your brain. They are aggregated in a small computational unit, the sort of core of an artificial neuron, that has some activation function. So there's some mathematical function inside the neuron that decides how to weigh the different inputs and decide what to send onwards to other neurons. So some signals come in, some computation is made to decide what to send onwards in the neural network. And backpropagation is essentially the idea that you can figure out how to adjust the weights and thresholds in the neuron in the most efficient way possible to get the desired outcome at the end of the neural network. So we're going to get into what supervised learning is and so forth. Key breakthrough in 1986, Hinton and Rumelhart came around. They stood on the shoulders of giants. Others had thought about backpropagation way before then. Like derivation was hardly a new thing. You could see sort of them putting together pieces, but it was still a substantial milestone in the development of AI. Jan LeCun, who today is the head of AI at Meta, formerly Facebook. Hinton, by the way, has been critical for Google for a long time. So you can see where sort of today's breakthroughs and today's commercial activities have been riding on ideas and insights already coined in the 80s and 90s. So convolutional neural nets, another one of those major things where Jan LeCun articulated this, and they realized already at the time that these things will probably work way better if they are larger, trained on more data, and if we had more compute. But they knew they were limited by the technology available at the time. So there was a pretty clear understanding that if we scale this up, it's gonna get better. So we're now up to, I guess, the starting point of the current golden age, the third golden age. There are some notable things that happened in the late 90s and early 2000s. I think Deep Blue beating humans in chess deserves a mention because at least I was very inspired by that. I read about that when I was very young. I think that made a big impression on me, but it was still considered kind of a winter or a dark age for AI. And then something happened towards the late, the sort of early 2000s, around 2008, 9, 10, 11, 12. And this was during my time as a student. So I was fortunate enough to see this up close. And basically what happened is people started thinking that maybe this is more of a scale and sort of size problem than had been previously recognized. I think there's been a tendency in the academic community to be drawn to the idea of elegant algorithms and sophisticated math, right? So people have tried support vector machines and feature engineering and sort of meticulous, complicated work. But more and more people realize that, okay, maybe with just enough parameters and enough data, we can learn without all these careful details. So that leads us to the 2012 AlexNet breakthrough. So actually, in order for AlexNet to happen, ImageNet first needed to happen. So Li Feifei, who started at Princeton and then finished ImageNet, I think, during her time at Stanford, they put together a massive image data set at the time. So ImageNet was, when it was released in 2009, it had more than 14 million images and 22,000 categories. And the academic community until that time had been starving with respect to data. And it's very, very hard to test what is possible in the limit of the current paradigm if you don't have huge data sets and a lot of compute. So through the foresight of Fei and others, ImageNet emerged, and that triggered an absolute revolution, because ImageNet then was the foundation for a competition where academic teams competed to produce the best computer vision algorithm. And until that time, algorithms that were based on some element of feature engineering and so forth was still dominating performance. But all that changed in 2012. So Krzyzewski, Sutskever, Hinton created what is known as AlexNet. And this was a huge triumph for kind of connectionism, or the idea that neurons that were connected in large networks with enough compute and parameters could learn very complicated tasks. So it was considered a massive breakthrough. It was trained on an impressive 2 GPUs, which gives you some perspective. Like, this is 13 years ago, and 2 GPUs was considered like, oh my God, it's so big. By the way, you notice Hinton here. They were at the University of Toronto in Canada at the time. Krzyzewski and Sutskever, I believe, are Krzyzewski, I think, is Ukrainian, who and studied in Israel. Sutskever is born in Russia, and then also, I believe, studied in Israel for a while, and then ended up in Canada. Again, I think we should remind ourselves that the key to progress is that there's talent all over the world that you need to take in and embrace in order to actually make huge breakthroughs. So Krzyzewski and Sutskever were absolutely fundamental to AlexNet. Sutskever then went on to become a co-founder of OpenAI, and that is more modern history, sort of. So I think this breakthrough cannot be underestimated, because around this time, and probably because of what Hinton was doing at Google, and a few years before this, Google also got into its head that they could build self-driving cars. There was the DARPA Grand Challenge, so again, the government going in and funding fundamental research. So the DARPA Grand Challenge was a competition to drive autonomously through the desert initially, and then on some roads, and then it was an urban version. And until that point, the perception part of self-driving had been a massive limitation. So cars essentially couldn't see well enough to drive, no matter what the cleverness was of the path planning and prediction and so forth. If you can't see the world around you, that's kind of a deal breaker. But with the rapid improvement of deep learning's ability to solve computer vision tasks, most notably the convolutional neural nets of the time, then performance increased dramatically. So then a bunch of companies basically jumped on this and said, all right, perception seems to be about to be solved. That could or would, should, I don't know, unlock autonomous driving. Waymo was created. A bunch of other self-driving startups came about. I guess, unfortunately, pretty much Waymo is the only one still standing from that time. A few more have followed and then actually survived to today. But it's an example, again, of when early scientific breakthroughs triggers a lot of excitement. Real progress is being made, and then it's a matter of like, how far can you take the improvement curve before you start seeing diminishing marginal improvement, or rather increasing marginal cost, because the first 80, 90, 99% of reality is usually quite cheap to understand. And this is what we're going to get back to. The problem again of reality is that almost nothing ever happened if you look closely enough. So that last percent, or whatever fraction of how we see reality, How different is it, and how important is that difference? That's what it's all about. Like the 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 big chunk of what we experience is rather straightforward to understand. So I don't dismiss the fact that most things can be automated. It's that there is a small uh, glue that holds things together that is extremely diverse and difficult to predict. Like there are always these edge cases, these rare instances, these things that we had not anticipated. And that's what usually breaks both business processes, human experiences. Like that part is the hard part. And automated driving has learned this the hard way. You know, most of driving works and is pretty simple. The problem is it only needs to fail a very small amount to be useless. In order to make sense of ImageNet and AlexNet, we have to understand the concept of supervised learning. So I think this is sort of at the heart of machine learning. And it touches on the question of what is it that we're learning? So in some sense, I think that machine learning can be described as three things, or at least there are three things that are important for it to work. Number one, there needs to be something to learn. So this might seem obvious, but actually there are a lot of phenomenon that or things that people imagine is something you can learn that may not actually have a ton of signal. So like there are fields that are high kind of conjecture and low evidence, like macroeconomics. People have um, a lot of opinions and ideas, conjectures about how the world works and what the relationship is between different things, but there's relatively weak evidence. There are other such domains. Psychology maybe is one. Um, um, so either way, the point is that in order for machine learning to work, there needs to be something you can learn. Number two is, can we sample this phenomenon? So is there a sensor or a collection device that is able to observe this phenomenon? So for digital things, that's pretty straightforward. But as you get into kind of medicine, for example, you may or may not be able to get the necessary samples out of, let's say, a human body. It's non-trivial to sample humans in that sense. So that sample that you get from the phenomenon you want to learn needs to be such that it reflects the necessary information to learn. So if the way we sense something or collect data from something um, um, loses too much information, we may not be able to learn the underlying phenomenon. And the third thing is we need to have a machine learning model that with enough data can in fact find kind of the parameters to kind of learn that phenomenon. So increasingly in the last 15 years, the last part, having a machine learning model able to learn, is less and less of a problem. There's still plenty of cases that are very difficult and it's still computationally incredibly expensive. But with enough data, the current understanding of things is that a lot of learning tasks can be solved using machine learning. But it's still far from obvious that we are able to sample reality to get enough data in many cases. So how does this work? Well, if we take a simple example, let's say we have shapes. We have squares, circles, and triangles, and we want to put them in piles. So we want a sorting mechanism. So we have our input raw data. So we have to be able to see and collect these shapes from somewhere. And we need to have a mapping. So we need to say this shape goes into this pile, this shape goes into this pile. This is the starting point for all machine learning projects. There's some raw input data, there's some desired output, and there's the We want some sort of mechanism in between that takes the raw input and provides us valuable and useful output. So I usually use the analogy of a music mix table when I talk about this. So you know these giant tables that music producers use? It has thousands of little knobs. And we're going to use that mix table as an analogy for the parameters in a machine learning model. So imagine you take one of the raw input shapes, let's say a square. We shove that into the mixer table, and then we carefully turn all the little knobs so that the square ends up in the square pile. So we shove it in, it goes through its little pipeline and should come out into the right pile. The idea is that the knobs in the mixer table, they represent little parameters in a neural network that, if carefully adjusted, makes the shape come out in the right pile. The challenge is that you want to shove one in and then take another one, and maybe this time, if it's a square again, it ends up in the wrong pile. Then you need to carefully adjust all the knobs without breaking what you did the first time. So this is the real challenge here. Is you want to find a parameter configuration so that every example ends up in the right pile at the same time. Because the danger is that if you over adjust to one example, a bunch of other ones will be wrong. So the tricky part is doing this for all possible inputs simultaneously in a very efficient way. And when I said earlier that there's been maybe less progress in models compared to compute and data, I mean basically that what we've done in the last 20 years very successfully, or even over a longer period of time, is we have now huge amounts of raw input data. We also have gigantic mix tables. Like modern neural networks have billions of parameters. There's even rumors of trillions of parameters in some cases. And we can turn a lot of knobs very, very quickly, thanks to modern GPUs. So basically, if you have access to enormous amounts of raw input data, you can create gigantic neural network models with billions of parameters, and you can turn them very quickly so that over weeks or months, you can actually learn to correctly process all the raw input data so that it ends up in the correct pile. This is commonly known as sort of supervised learning, where you have inputs and desired outputs. You could also imagine that you design something where the model is optimizing for separation of things. So basically, if you have a big bunch of raw inputs and you can describe some similarity metric between them, then you could have the model independently figure out what the optimal way is to maximize the separation between things. So everything that is of one particular category ends up in one pile, and so forth for the other piles. That could, in some sense, be called unsupervised learning, where you, through observation, infer the appropriate method. However, I have to emphasize that defining the similarity metric still requires human intervention. So I've always been of the opinion that all learning is supervised in some sense. And there's a bit of debate about this, but that's my position. So I think all learning is supervised. There has to be some objective function, something we want to maximize, and that's always a choice. You could debate whether there's free will and whether we actually choose or not, but there is some objective function coming from somewhere. Sometimes it's nature, sometimes it's society or social structures or business problems. Either way, a lot of machine learning is about optimizing behavior. So learning patterns from data, so figuring out what the properties of these raw inputs are, such that you can correctly place them in the desired output buckets, And you do that by basically brute forcing your way to a set of parameters, turning a bunch of knobs. There's another concept that deserves an introduction at this point. And if we come back to the problem of making rare things common, how do you do that? Well, a lot of it is about kind of figuring out how to decide if two things are similar or not, right? So we talked about it that a second ago where we said you can sort of do unsupervised learning if you have some similarity metric. So if you can take two things and make a statement about how similar they are, that's informative, right? So if we go into the language domain, there's like 50,000 reasonably common English words. Americans apparently use 20 and British people quite a bit more, but you know, let's say there's 20,000 words that matter. If you just take a token, a word at face value, every character is a unique word, and two words are essentially orthogonal. So they are in some sense infinitely different. If you replace one word with another word, the sentence is now totally different and unique. I mean, I'm saying that's an option we have. Clearly, that's not how it works. Like, a lot of words are interchangeable. So we can use two similar words in a similar position, and the sentence still makes sense, right? So if we go back in time, if you wanted to learn a sequence of words, the problem is that you can put together a sentence, a sequence, in many, many, many different ways, right? The number of possible permutations, if you have 10 words and 20,000 options in the dictionary, is huge. And of course, there's like grammar and structure and such that limits the space of possible sentences, but it's still very, very big. Like what I said to you now in the last 30 seconds has probably never been said in exactly that order before, and will probably never be said in that particular order again, or at least the probability is very small. So this ties back into the problem of reality, is that nothing ever happens, at least not twice, right? So most things are very rare. How can we make them less rare? So since a long time, there's been the idea that words are in some sense defined by the company they keep. So how can we use this realization? Well, I'm going to walk you through three things that are on the screen here. And it's going to be a little bit of a mindfuck, so you'll have to pay attention. The first thing is, let's assume we build what is known as a co-occurrence matrix. So that's kind of a spreadsheet where the columns and the rows are words. The quick brown fox jumps. And if two words occur in the same sentence, we increment that cell with a 1. So we put a 1 there. Okay, so we have our co-occurrence matrix. Let's now try and read like basically all of the internet, okay? Like as much as we can, trillions of tokens preferably, so that we have a very detailed understanding of how words occur together. That's step number 1. That's the co-occurrence matrix. Step number 2 is, and this is where it gets a bit mathy and kind of complicated, but I'm going to try and be gentle. Imagine you take the sphere. So in this case, let's do 3 dimensions. And let's anchor everything by placing the word "the" as a point on the surface of this sphere, right? So there's a point on the sphere that we say, this is a representation of the word "the," right? And then we're going to try and place all other words on the surface of this sphere, such that the cosine distance between two words is proportional to how often they occur in the same sentence. So what does that mean? So first of all, a cosine distance or an angular distance is like in the example here with the orange and the apple. Imagine they are 2 points. There's going to be an angle that separates them. So what I've described now is kind of like a huge optimization problem. Because if we move one word, the impact is that all other words that it occurs with needs to be moved a little bit as well. So we want to kind of globally solve this for all words simultaneously. And there were some major breakthroughs in this. The origins of the idea was actually came out of stuff that Hinton wrote about sort of distributed representations and dense representations. Then Joshua Bengio made some major advances in this in the early 2000s. And then it was massively popularized due to work by Thomas Mikolov. He was at Google. I think it was around 2012 where Word2Vec came out. So Word2Vec was this simplified way to basically take a large amount of text and infer embeddings, basically vectors that could represent each word, and with a much lower dimensionality than just a giant matrix of a dictionary. So like if a word is just a 1 or a 0, depending on whether it's a specific word in a dictionary, most cells in that big spreadsheet that represent a sentence is going to be a 0. And lots of zeros is bad for computers, right? We want smaller spreadsheets, so fewer dimensions, fewer columns and rows, with more numbers in them. So a denser representation, where small changes don't have kind of catastrophic impact. So if we replace two words that are similar on the sphere of this ball here, the embedding sphere, the sentence should still mean roughly the same thing. So if we replace orange with yellow, it's different, but it's maybe not like dramatically different, right? Or if in some context it's either a horse or a pony. Those are similar things. They are different. They have some different properties, but depending on the context, the difference can be important. But in a lot of cases, the difference is not actually that important. And suddenly we've made sentences on an abstract level occur much more frequently, right? So because we can sort of abstract away some of the sparseness, the rarity of things, compact it down and make it denser, there will be more noticeable patterns, right? So this was a major breakthrough that we're still riding on today. And it can be expanded into basically any domain where objects occur in a context. It's not limited to words in sentences. It can be anything. It can be songs that people listen to on Spotify, for example. So if a bunch of people listen to roughly the same songs, they kind of occur in some context, you can represent each song with an embedding. And if another person listens to a bunch of similar songs, the probability is that other songs in the same area on the surface of this sphere will fit in for that person. So the same idea is transferable into many different domains. Now that we've been introduced to this concept, we can add a bit more kind of technical description to it. It's still very high level, but so imagine you have a bunch of words: cat, kitten, dog, house, man, woman, king, queen. You can think of the denser representation as representing some dimensions that are important to understand what an object is. And you can then use dimensionality reduction essentially to put things that are similar along some dimension next to each other. So cat and kitten ends up close to each other, dog is over on one side, house on another. And basically all animals at some level should be grouped together, while objects like a house or a car maybe is in a different part of the surface. And then depending on when you do the dimensionality reduction, you can choose which dimensions you focus on to kind of maximize separation along some axis. And it turns out this preserves some fascinating semantic meaning. So this is a major, like, mind-blowing experience for me. These results came when I was in the beginning of my career as a machine learning engineer. I was working on natural language, and it became clear to me that these word embeddings, they preserve semantic meaning. And what do I mean by that? Well, turns out if you take the vector for man and the vector for woman, so 2 points on that sphere, and you walk between them, the path, so the vector between the two, is going to be roughly the same as the vector between king and queen. Boom, right? That's pretty amazing. So that means that relative positions in embedding space on this sphere, high dimensional sphere, preserve some semantic meaning. Similar example that was popular at the time was like countries and capitals. Apparently they occur in such a way in text that their relative position on the surface of this high dimensional sphere is similar. Of course, it's not like exactly the same, but it's very, very close. So from this, you could start imagining that, okay, if we find the appropriate dense representations, there are tons of patterns that will emerge and be more accessible and visible inside the structure of all this data. So if we just find enough information, if we download enough of the internet, maybe human-like natural language abilities will start emerging. Okay, so we've learned now about dense representations and sort of embeddings and how they serve as a way to make rare things common. So these breakthroughs came along early 2000s, 2010s, but we saw that there was an upper limit to how far we could take this. And in order to understand those limitations, I think we have to challenge ourselves first. So help me. When I tell you that, you start predicting things in your brain, right? You're confused, you're not sure, what does he want me to do? Help with what? Help me. And you might imagine different ways to finish that sentence, right? So humans always predict a little bit into the future. And with very little context, with a very small number of words, it's very hard to know what's going to come next, right? If I add a bit and say, help me predict, what came into your mind? So when I do this with a live audience, the most common thing is predict the future. That's what people would all appreciate if someone could do, right? In this case, I'm going to continue the sentence with, help me predict the next word in this sentence. And if you're British, you add please, right? So there's some constant prediction engine running in our brain, right? We have some experience from what we've seen and done in the past. Some engine in our brain takes that experience and whatever small steps we have of context, first few words, some object that has started moving across our field of vision, and we immediately aggressively predict what's going to happen. Some of you have probably seen these visual illusions where the brain is like actively filling out things that we may or may not see, to the point where like you can trick it quite easily because it's so aggressively pattern matching. And this is because, we want to be constantly ready to act on new information. So if you want to go a bit more into the philosophical side here, people like Kahneman, who has written a lot about sort of what are the different modes of thinking in our brain. A popular mental model is that there's kind of type 1 thinking, which is the immediate, the reflexes, the instinct. So our pattern matching engine is constantly running, constantly making predictions, and we just like immediately react to things. And that's a necessary part of functioning as a human in our natural reality, right? And then something that we believe to be a particular superpower of humans is that there's also kind of a type 2 system of thinking where we don't just make intuitive predictions of the next frame or word or situation. We also can sort of do search in possible futures and imagine different alternatives and maintain those different alternatives in our short-term memory to evaluate which possible future is either desirable or most likely, or if there's like maybe there's a couple of steps that are intuitively probable, but then at some point you can kind of look at some long-term effect and realize that, okay, likely it's going to be this instead. So the intuitive short-term prediction may be wrong if you think along a long enough timeline. So there's all this stuff going on in our brain that we still don't know quite how it works, but that we're trying to replicate in computers. So embeddings gets us some way towards the goal of generalization here. It means we can replace words in a sentence without kind of starting from scratch when trying to understand the sentence. But it's too static. So if every word has a unique embedding, so a dense representation that we use everywhere all the time, some nuance is lost, right? And as anyone who's been in a relationship knows, words can mean different things depending on context, right? So there is not such a thing as like a static, unique embedding that correctly captures the meaning of a word. The other words in the sentence also matter, right? So the realization that embeddings were not nuanced enough contributed to what has been the most important breakthrough for the rapid advance in language models that we're experiencing now to come about. So in 2017, researchers at Google published a paper called "Attention is All You Need," and it introduced the idea of what is known as a transformer. So basically, a transformer is a form of neural network that takes an embedding of text as input and tries to predict the next word. And the trick or the key to why they have become super successful is they realize that if we sort of bend the embedding based on the context, make it, adjust it a little bit, kind of push the word slightly to a different point on that sphere we mentioned earlier, depending on context, we can unlock a totally new level of subtlety and nuance in predicting language. So instead of just saying, let's predict the next word, here are a bunch of words, they all have a representation that is an embedding, great, huge improvement in making rare things common, but let's like adjust the embeddings a bit based on what has been in the context before. So to visualize this, you can imagine sort of that in a sentence like the animal didn't cross the street because it was too scared. It in that sentence clearly depends on other words in the sentence. To correctly understand it, you can't just use like a universal embedding for the word it, because it means different things all the time. And in this case, it basically means the animal. Humans can infer this. It's pretty obvious to us. But if you imagine you had tried to learn to understand this sentence, and if you were forced to treat it as a context independent word, you'd be lost. Like, you're basically gonna fail if you do that. And this dependency between words is like absolutely not a new insight. So again, going back to my own experience, when I got into natural language processing, the quote unquote previous generation of NLP, natural language processing, emphasized things like understanding the underlying structure of language in an explicit way, right? So when we grow up, we learn language through interaction. And then we go to school and we're told that, like, oh, by the way, there's like a bunch of rules for language. And that can improve our ability to express ourselves, perhaps. But I don't know if it really changes how people talk or think. Like, the fact that there are nouns and verbs and so forth, I think is, I've thought a lot about sort of, does that matter to most people? And the answer is probably no. But at some point, we believe that if we could just learn to correctly identify things as nouns, verbs, and whatever other parts of speech there are, we could find patterns in language through that. And this is kind of illustrating the very long history of conflict between some amount of knowledge and expertise versus just brute forcing from patterns, right? So for a long time, we believed that by understanding the structure of language, we could inject enough expertise to overcome the sparsity problem, to basically handle the fact that there are so many variations possible. So the rules we imagined could help us handle the sparsity. So here are some examples. Obama used to be president of the United States. I wish he still was. There are nouns and verbs and things in there. Some of them we can think of as named entities. So like Obama is a person, United States is a location, and there's also co-references. So here are two sentences. When put in a sequence, we can infer that he in the second sentence is referring to Obama. And that's, if we go back, exactly what we essentially are doing in the example with the animal crossing the street. It is dependent on the previous mention of the animal. So there is a noun in here, and there's a co-reference relationship between that entity, the animal, and it, as it's being referred to later in the sentence. So it's not like attention and transformers. Again, everyone is constantly building on previous results, and giants on giants on giants. It's turtles all the way down. But the idea was that, okay, can we through attention and embeddings basically brute force our way to enough pattern understanding to replicate human language in a way that is indistinguishable from an actual human. To go one step further, just to kind of set the stage for the next step, language researchers realized that there's all these dependencies going on in language, where it's not just that there is like co-reference mentions of nouns like Obama and he. There's tons of like connections between words that have emerged from our human interactions. So president of the is like a modifier to the compound noun of United States, right? So there's two words that together delimit a country, a noun, an entity. There's the concept of the president, and that president of something kind of becomes a thing. There's a subject to all of this, which is Obama, and there is some time indication in this case, used to be. So that's a verb with a modifier of like, okay, so some entity is related to some other entity, and there's an expression of past tense that connects the two and places it in time. So a lot is going on here, right? So at one point I was working on developing machine learning systems to understand these relationships between entities. And it turns out that most of the expert attempts we made 10, 15, 20 years ago have now been basically blown out of the water by methods that just take huge amounts of data and infer this structure using attention. So there is no explicit training of the task of figuring out what is an entity and what is a modifier and what is the subject and the object of that and so forth. So this goes back to the core challenge of generalization, right? The goal of machine learning is to solve tasks by learning from patterns in data such that we can take on new tasks with unseen input that we have not explicitly experienced during training. And transformers and attention is more powerful than these explicit things where we try and learn some sort of intermediate task. By just focusing on predicting the next word, conditioned on preceding words, this structure emerges through volume, essentially. And people did not just like arrive at transformers out of thin air. There were generations of previous attempts. And without going into every detailed permutation of this, there was initially something, or at one point something referred to as recurring neural networks. So basically you had a network that was feeding into itself. So you tried to just predict the next item in a sequence over and over and over again. That was based on basically static embeddings and some amount of like memory-ish, but not much. And then there was long-term, short-term memory, which is awfully similar to the idea of attention, where you wanted to kind of keep some signal with you for some period of time. So when you processed and predicted the next word, you took into account what you'd seen earlier, both far back and not so far back. So long term and short term. Again, I'm not going to go into all the details, but like if you abstract a few levels, essentially there was the seeds of transformers came from RNNs, then LSTMs, and then the multi-headed attention sort of mechanism that was introduced with transformers. And there's been a lot of underlying progress on encoding, which is again kind of going from high dimensional data to lower dimensional data. If you have going from words to embeddings, you can try and find even lower dimensional representations to further enhance your ability to see patterns. And ultimately what you're trying to do is squeeze every little bit of signal out of the data you can. So if there is structure in that data, you're like, these models are pretty fucking determined to find it, right? To the point where it can pretty much approximate anything at this point in language, in my opinion. I think that most of the structure you can express using words, a large enough transformer will learn. So the challenge is no longer can we learn these things, it's is the learning we are doing useful, right? So this, as we get into prediction mode in a moment, could indicate that there is like an upper bound where we've saturated these networks with all the available information that is out there in text. I basically think we're running out of text. There's a lot of it, but we've also put most of it into these systems now. And if there's signal there, they can learn it. They can find it. They are like bloodhounds for signal. Signal is essentially patterns, right? So if there's a pattern, these models will find it. We've covered now kind of the rough history of machine learning and AI, the recent breakthroughs with the introduction of dense representations, so embeddings, the creation of ImageNet that led to AlexNet, which demonstrated that large connectionist kind of models like neural networks with enough data and compute could become the state-of-the-art method to understand data, to learn patterns from data, and to solve tasks. And it was also demonstrated they could generalize. So there's one parallel concept here that we haven't covered that is relevant to kind of tie it all together and look into the future, and that is reinforcement learning / and search, if you will. So in some sense, reinforcement learning to me is also supervised learning, with the difference that the supervision comes in the form as a reward. So rather than try and classify objects into different categories or predict the next word based on previously seen sequences of words, we want to anticipate some reward. So let's put this in a human context. Imagine you are an agent. So you are someone who can take action. So there's an action space. That's all the available actions. We obviously have a very large action space. And then social convention and norms and so forth limit that space. And some physics too. I mean, I can't fly, but I'd love to. I can, however, take off all my clothes and run naked through the street. I may or may not choose to do that. Why? Because there's an environment, the world in which I operate, and it gives me feedback in the form of rewards, right? So our environment has a state. There's objects and people and relationships and things. And as we take action, the state of the environment is updated and we get some feedback. And some of that feedback is sort of immediate and short term, and some of it is more long-term dependent. So if you're young and you are faced with doing your homework or watching television, you will have immediate feedback from watching television. Maybe you feel good and it's relaxing and nice. But there is a slightly longer term feedback of getting to school the next day and failing a test because you haven't done your homework, or having your parents get angry with you because you haven't studied. So clearly humans evolved to understand how a sequence of actions will influence the environment and what the resulting reward could be expected to be, right? So the same underlying thinking is true in this case here as well, of rare things being hard, right? So stuff that happens all the time, it's easy for us to predict how an action translates into a new state and a reward. If I'm hungry, I eat, my body tells me I'm full. It's a very clear feedback loop. It becomes obvious to us at a very early age. It's not very complicated. Predicting those kinds of cause and effects is trivial, essentially. But then as you grow up, you're faced with increasingly complex and difficult to predict problems. Should I go on a second date with this person? What will happen 2 years from now if I continue in this relationship? Or what business strategy will lead to the most profits? Or what research problem is most important or interesting in the next 10 years? those things are incredibly difficult to predict, to the point where you might even ask yourself, is there even an element of skill there, or is it mostly random, right? I mean, humans, and especially smart humans, would like to think that through our amazing intellect, we can analyze the situation, take action such that we can predict the long-term state of the environment and maximize our reward. Yeah, sure. And entrepreneurs especially build the future. That's the mindset. But also, like, there's so many people who have strong vision, a lot of determination, and just are wrong about the future. They misunderstand or are unable to predict the impact of actions, or the world is just so unpredictable if you go far enough into the future that no amount of intelligence or skill maybe can overcome it. And we're going to dwell on that because to me that's a critical question for the limits of AI and what we can expect in the future. If we think there is basically no upper bound to how far into the future you can predict if you just get smarter and smarter, then of course super intelligence or advanced machine intelligence or machine, whatever we call it, will have a major advantage. I suspect, and we're going to talk more about this, that the correlation between intelligence and success is weaker than people think, probably because this reinforcement loop of actions, environments, and rewards quickly gets very, very difficult to predict. It's essentially chaotic. And the definition of chaos is that the approximate present does not give you the ability to predict the approximate future. Either way, reinforcement learning is a thing. Just gonna put that out there. So there were breakthroughs in the last 20 years where DeepMind in particular was a pioneer of reinforcement learning, still is. They managed to train AI systems to play various games. And that makes sense, right? So the benefit of most games, like take chess, for example, it is known as a perfect information game. So in chess, you have a clearly defined set of pieces. You have clearly defined rules for how those pieces move. There's a clearly defined win criteria. You know that there are two agents that will take turns to take actions. The environment can be perfectly observed all the time, in that all the pieces have known positions to you. No one is hiding parts of the chessboard. And you take turns, and there is a clear terminal condition for the game where either you win, your opponent wins, or there's a remis, a draw. So this is an excellent type of problem to address using reinforcement learning, where you want to try and figure out what the reward is from taking a sequence of actions that constantly updates the state such that you win in the end. And it helps a lot that it's perfect information and that there's clearly defined rules, there's a finite set of possible actions, and there's a clear sort of goal of the game. To compare this to the human experience, we have no idea what the actual action space is. We can barely observe the environment, and who the hell knows what the reward is at the end of the game, right? Is it 42? Is money the high score of life? Should we all become Zen Buddhist monks and sit in a temple until we die? I don't know. There's some ambiguity and complexity to this that I think plays a major role in what can be expected of machine intelligence. clearly humans make very important choices about long-term versus short-term, for example. Um, you could imagine that if you had a short-term optimization target, doing cocaine or drugs is great, because like it's probably amazing for a couple of days or weeks or a month. I don't know, haven't really tried, but you could imagine that's pretty exciting. The downside is that like most people who do drugs die eventually or become miserable. So if you consider the reward over an extended period of time, the short-term relaxation and euphoria, most people come to the conclusion that like, yeah, maybe nice, but like, look at this long timeline. I want to do other stuff than be, dead, right? Um, Companies navigate this space all the time. You can make short-term business priorities, preserving cash flow, optimizing for liquidity. The simple solution is just don't do any R&D, don't develop your products. Feels nice for maybe a year. You can maximize profits, and then 2, 3, 4, 5 years down the road, you're irrelevant and go bankrupt. Others have a very successful business selling, for example, electric vehicles, but think far into the future and realize that the real money is in maybe robotics or something else. So they're prepared to basically gamble the entire existing business on a long-term vision for something different. And then Wall Street might have one opinion, and science optimists have a totally different opinion, right? Hypothetical example. There have been several highly publicized breakthroughs in reinforcement learning. I think the perhaps one of the most important ones is in 2016. Google's DeepMind department defeated Lee Sedol in Go, and that was considered kind of the last game that humans were still better at. So chess, Deep Blue, the IBM solution, it beat Garry Kasparov already in 1997, but then it took another almost 20 years to solve Go using computers. And since then, as far as I'm aware, there are really no perfect information games where humans stand a chance against computers. Like your smartphone will beat the world champion in chess without even heating up today. Like chess engines are just massively superior to humans, and various reinforcement learning systems have now beat humans in all sorts of games. StarCraft, Dota, and others have been popular kind of experimentation grounds for this. And the common denominator for all these problems is that they are, or games, is that they are perfect information games with clearly defined rules and some finite amount of possible actions and a pretty clear terminal sort of condition or win criteria. So now we can start putting things together. And the current state of the art is a mixture of many things. And this is, again, I'm doing this partly to make sure I have the correct understanding myself. But the way I understand it, based on all the reading I've done, is we depend on transformers as a kind of going back to Kahneman's type 1, type 2 thinking. That's where the vast majority of sort of pre-training, which is what is done in these giant GPU farms. You take tons of data, you find sort of subtle embeddings, you contextualize things, you have to do a lot of knob turning, and you get these giant kind of billions of parameters, large models, large language models that have inferred some sort of understanding of language that also contains some understanding of the world, but only through its ability to understand the relationship between words. And I say understand by, that's a very generous way of putting it. What it's able to do is estimate the conditional probability. So conditional probability is like, if this, then that. So if these things occur in this way, then these things should occur in this way. And it has it's the understanding is limited to sampling out of those probabilities. So it estimates some distribution, which is like, how probable is it that stuff will happen in a certain way? And then based on the set of context tokens it gets, it selects the most likely one. And that's it. It's tempting to anthropomorphize, which is to give sort of infer human properties, to give human attributes to machines. It understands or whatever. When you break it down mechanically, it's a process that predicts the next token. And it can do so many, many times, auto-regressively, so over and over and over again. And it can consider a very long context window, and it has been trained on a massive amount of data. But there's no magic in there. It's like, that's what it does. And then you can add to that an element of reinforcement learning, where you optimize a policy to basically predict how a user or a human will value an output. So this can be used to balance models being harmful and helpful. So if you ask it for an itinerary to enjoy Paris, it should be helpful. But if you ask it to give you the recipe for a biological weapon, it should refuse. And all of the data out there on the internet is going to lead to certain abilities. And if you want to put guardrails in place, there are some different options. You can try and remove that from the training data corpus, which may or may not be possible. You can try to add sort of a protection mechanism that you train using human feedback. And you say, okay, based on this model output, what do you think the human will think about that? And you try and learn such a policy. And then you can steer the underlying model to avoid output that you don't think humans will appreciate. And then you can add some element of search to this. So that's going to bring us into what is known as chain of thought, which is essentially a way of doing search. So you've all probably seen recent excitement about DeepSeek or OpenAI's O-series models that think. So how do they think? So this brings us up to, I guess, what is currently the state-of-the-art methodology to get increasingly sophisticated behavior out of language models. And it's known as chain of thought. So basically, chain of thought came out of Google, again, another Google innovation. And it's surprisingly simple. When I first read about it, I was not sure if I'd understood the paper, because essentially what it's about is that you take a prompt, so a question you have to an LLM, but rather than just ask a question, you instruct the model to decompose the question into smaller substeps and push it to do intermediate reasoning, and then finally integrate those intermediate reasoning steps into a final result. So if you ask it a question, the goal is to make it think, therefore I think, therefore I think, therefore I think, so the answer is, and then whatever the answer is. This can be anything from counting to solving reasoning problems. And essentially, improves the model's ability to figure out the appropriate solution. How exactly that works? Well, I guess you could intuitively imagine that there's some amount of context in the training data that if the model expresses a reasoning step as well as possible, will match better to something it's seen in the training data on the abstract level. So remember, we are abstracting away exact words here and instead focusing on the underlying structure that we talked about with embeddings and attention and so forth. So this is proven to be very powerful. It elicits reasoning. So these models are known as reasoning models, or the popular term is that they are thinking models. So OpenAI has famously released its O-series models that do this. And essentially they've taken this further and further, where you can ask an LLM many different questions based on a single starting prompt. So it's about how many sort of reasoning tokens you use. How many times are you asking the model, and how many dimensions of the problem can you push the system to explore, such that the integrated final answer is the best possible. So this obviously increases cost. It's sometimes referred to inference time compute. So basically you're not doing training, you're doing inference many times. You're basically predicting sequences over and over based on different prompts, and then take all of that and integrate it into a single response. And there's been a lot of innovation in this area in a very short amount of time. There was a big fuss not long ago about DeepSeek. So DeepSeek is probably the most important attribute of DeepSeek is that it's Chinese, which makes it very scary to Americans. But if we look beyond their origin, what they essentially did in the technology side of things is a brutally simple approach to improved chain of thought reasoning. So there's a giant diagram for how they did this, but the shorter version is that you can use reinforcement learning that we talked about earlier to essentially steer a language model to produce chain of thoughts, so sequences of decomposed questions and sort of intermediate reasoning steps that it expects the user to appreciate. So if you go back to the reinforcement learning approach, there's a reward function that tries to learn the user's appreciation of an answer. So that's the feedback, the reward function. And the action it can take is a chain of thought, so a sequence of intermediate reasoning steps. And in the traditional approach, you have neural reward models. So basically another neural network is trained separate from when you train the LLM, and it's learning user reward feedback. What DeepSeek did is they made an extremely simple version of this kind of feedback. They basically did binary checks like answer correctness. So they took math problems and code problems that you can know definitively whether they are right or wrong. They checked for formatting, they checked language consistency, and through this way they could improve the underlying LLM's ability to produce valuable chains of thought through reinforcement learning, massively improving the underlying model's ability to solve problems. And they demonstrated there's a nice scaling law for this too, where the more reinforcement learning training they do, the better it gets. There are also several other things they did, like rejection sampling. So they basically threw away a lot of the chains of thought that they produced based on these kind of rules. They had many different levels of like fiddling around with this. Again, this is not explicitly a presentation about all the details of how DeepSeek did chain of thought reasoning with reinforcement learning. My point is just that this is now one of the major areas of innovation. I think the current bleeding edge of language model research, at least in the applied sense at these AI labs, appears to be in the area of how can we improve chain of thought reasoning, reduce the cost of that, and generally make the models able to think longer without massively increasing costs. So that means we've established a few different paradigms or phases of training. There's pre-training or just training, I guess. It's kind of weird to me why it's called pre-training. I tried to look that up and I'm not sure I understand why they call it pre-training. Either way, there is a step where you basically bring out the huge GPU farms. You just turn the knobs for weeks and months, and you inject web scale amounts of text, right? So this is the big training phase. This is very expensive. It's where you can easily spend tens of millions of dollars or even hundreds of millions. Supposedly the largest models are, in the many hundreds of millions, maybe even $1 billion, which in pure compute is pretty crazy. But it's because they have so many parameters and there's so many tokens and so many conditional probabilities that you can search through and sort of fine-tune based on, that it's worth it to take all that time and money, supposedly. And then there's a next level of or a quote-unquote lower level, which is supervised fine-tuning. So you have humans give feedback to the model to tell it which answer it prefers. So maybe you sample the model a few times and you pick which answers you think are best. You can do policy gradient based on this. So basically you can modify the underlying LLM based on the feedback you get through supervised fine-tuning, either by training a separate reinforcement learning model or directly. And then the last step of this is the sort of stuff that DeepSeek has shown, where you can do rule-based reinforcement learning fine-tuning, which avoids the need for a human intervention, but it can only be applied to things that have sort of programmatic reward functions. So where there is a known answer, a math problem or a coding problem or something like that. So now we're more or less where the state of the art is with respect to language models, as far as I understand it. So that brings us to the challenging question of, can we now predict the future? Where is all of this going? Are we going to get AGI in the next year, 5 years? When is that going to happen? Well, I try to focus on the things that I do know. And I think there are a couple of things we do know. Number one, modern machine learning systems are essentially perfect approximators. So what do I mean by that? Well, if there is signal in data, these models can learn it. They will find it and they will learn it. So if in this sequence of things, there is pattern enough that you can reliably predict a token based on the training data, these models will find it. And that's pretty significant, right? It basically means that anything we can write down and structure that has an underlying pattern. So there needs to be a phenomena we can observe, but assuming there is such a phenomena, these models can learn it, okay? So then the question is, how far can we take this paradigm and where will it take us? So the race in the last 5 years, ever since we sort of discovered this, has been to bring all of the internet into these models. So Ilya Sutskever, he famously called web scale data the fossil fuel of AI. So there's only so much oil sort of out there. We can pump it out of the web servers all over the world, but we're not getting new material at nearly the same rate as we are consuming it right now. So the consequence is that there are major companies that are basically just producing and codifying human knowledge. To some extent, Cognic is an example of that, where there's a bunch of human knowledge that we have that is not available as an online data set. Like driving is not easily inferred from the internet. How do you drive a car? It's not like there's some videos of driving, but the pedals, the gear shift, the blinkers, that requires real world data or very domain specific data that is generated through either simulation. That too has limitations because you can only simulate some percentage of reality so far. Like we wish in self-driving cars, we wish we had a matrix Docker container, but we don't. So we need real world data and we need human evaluation of behavior. But there's still plenty of stuff that we can bring into these systems. So companies are springing up vertically now that focus on extracting as much human knowledge as possible and pushing it into these kinds of models. We can also see the reasoning paradigm continue evolving for quite some time, I think. Basically letting LLMs recursively work on a problem for a longer time. That can, with some cleverness, maybe continue to bring improvements for a while. There is the risk that we will hit some sort of diminishing return and we may in fact be on an S-curve. Had it not been for the reasoning breakthrough, the underlying sort of pre-training step of LLMs was showing very noticeable leveling off, kind of, whether because of the lack of novel text data or other reasons is constantly debated right now. Reasoning is providing another kind of trajectory of scaling. And of course, there's now tens of thousands, hundreds of thousands of very talented engineers and researchers focusing their attention on this, which most likely is going to bring many more improvements and leaps. At the same time, when I look at the world, I feel like most people engaged in AI today are engaged on a relatively superficial level. I'm a bit elitist in that, I guess. Some might disagree, but the underlying science of this is obviously moving slower right now than the applied level, in my opinion. We are seeing many engineering breakthroughs, but fewer scientific breakthroughs. And there are some directions that are pointed out that I'm going to probably make some more videos about. Obviously, I'm passionate about embodied AI and physical AI, which has many challenges that are not part of the virtual problem of LLMs. There's also contrarian views on how to do this, like Jan LeCun has proposed JEPA, which is a different kind of prediction model that works more in latent spaces. So basically through embeddings, sort of joint embeddings. So there are plenty of ideas out there, many more than what I just mentioned, many more problems than I just mentioned. Ultimately, I hope this presentation has given you sort of a quick run through of the history of machine learning and AI and some idea of where the bleeding edge is today, at least in terms of LLMs. And I look forward to making more videos about AI and sharing them with you in the next couple of weeks and months.